Pleasant day to everyone. Today we're going to discuss a supplemental lecture for Module 3 of the subject CE4111, Highways and Railroad Engineering. So for vertical alignment of roads, we'll be discussing in this lecture the application of the sight distances for undercrossings on sag vertical curves and the application of alignments for both horizontal and vertical alignment. So as we have mentioned earlier, for sub-vertical curves, there are some instances wherein there are what we call undercrossings or underpass. So kung wala ito, yung ginagamit natin would be the equations that I have just mentioned. So for undercrossing or underpass, the sight distance now on the highway will have separation or grid separations. And at this point, the sight distance should be at least as long as the minimum stopping sight distance, or preferably longer. So while the existence of such structures or fascia structures is not frequent or not usually common, it may cut the existence of this structure could cut down the line of sight of the driver approaching the sag curve, and thus limiting his vision and limiting the sight distance to less than otherwise attainable or desirable. Therefore, it is generally practical for us now to provide the minimum length of a sag vertical curve at a grid separation wherein there are existing structures. And there would be recommended grids exceeding this. So let's solve an example. An equal tangent sag curve has an initial grade of negative 4% and a final grade of positive 3%, and a length of 1,270 feet. An overpass is to be placed or built directly above the point of vertical intersection. So we have to determine the height at which the bottom of the sign or of the overpass is to be placed above the roadway. So to begin with, we summarize our given values. We have a negative to positive grade section. So we'll have a sub-vertical curve. We're also given the length of the vertical curve at 1,270 feet. So we can now solve for your A from the given grades. And this is simply the absolute value of the difference of grade 1 and grade 2. So we'll be arriving at the value of 7. So for our required, we are to solve for the clearance or height between, or the distance between the roadway and the bottom of the overpass or the sign of the overpass. So since this is now an example of undercrossings or underpass, then we will use H1 equal to 8 feet and H2 equal to 0.5 feet. So these values would come from our AASHTO 2011 guideline. So for our solution, since this is clearance or involving clearances for underpass or undercrossings, then we will use the equations for crossings. So for the first case, that is when the sight distance is less than L, we use this equation. And the other case is when S is greater than the length. So we follow this equation. So we cannot directly solve our problem using this equation since we are given L, but the sight distance S and the vertical clearance HC or C is unknown. So we have two unknowns and we'll only have one equation. So to solve here, we have to determine first the value of our sight or stopping sight distance from table 3.36 of the AASHTO 2011 manual. Okay, so with that, to use the table, we have to solve for the value of K by using the equation L equal to K times A. So we know L, we know A. So just substitute the values. So the K to be computed, that will be computed is 181.429 feet. So with that, given table 336, the K value that we have solved is 181. So from there, we look now on, we're given feet, so we use the US customary values. So we look on the design value of K, which is 181. And we have here the value of 181. Okay. So with that, it means that our design speed will be at 70 miles per hour, and our design stopping sight distance will be 730 feet. Okay, so given now our design speed, your stopping sight distance, and the given length 1,270 feet, we can now assume or use the values or the equation for the length or the sight distance with undercrossings. So let's use first S less than L. So we have this equation. So L now is 1,270. Or simplifying, first, each one is 8 feet, each 2 is 0.5. So if we simplify it, ito na yun. Okay? So pag walang given na value for each one and each 2, ito na yung gagamitin nating equation. But if there are other given values for each one and each 2, you use the general equation. Okay, so with this, we now know your A. We have identified SSD from the table. So we can now solve for C. So C now is simply equal to AS squared over 800L plus 5. So substituting our values, we arrive at C equal to 8.67 feet. So supposedly, the clearance or the vertical clearance between the roadway and the undercrossing or the overpass, the bottom of the overpass should be 8.67 feet. But according to AASHTO 2011, the recommended minimum clearance for undercrossings is at 14.5 feet. So therefore, instead of using the computed value of C, then we use the value recommended. So the minimum value recommended. And then if we want a safer clearance on our underpass or undercrossing, then we could apply a C, which is equal to 16 point or a exact 16 feet vertical clearance. Okay, so this is just the minimum. You can have it greater than 14.5. Okay, so let's have another example or application of vertical alignment and in coordination with the horizontal alignment. So we have here our plan view and the profile view for the horizontal and vertical alignments of a road section. So this is a two-lane highway with road width or lane width at 3.5 meters and a posted limit of 80 kilometers per hour. And on one section, it has both a horizontal and vertical curve. So this section, okay, is composed of both horizontal and vertical sections. So a recent daytime crash wherein the driver traveling eastbound, so papunta dito, eastbound, strikes a stationary roadway object, which resulted to a fatality and a lawsuit alleging that the 80 km/h posted speed limit is unsafe for the curve in question or for the section in question. And is the major cause of the crash. So as the highway engineer, evaluate and comment on the roadway design. Is there a problem on the geometric design? Is the posted 80 km per hour speed limit really the cause of the accident? Okay, so for our analysis, we uh, we divide it into two, which is your horizontal alignment and the vertical alignment. So let's start first by checking the horizontal alignment of the road section. So given now the plan view, we have your point of curvature and the point of tangency. So from here, we'll be able to get now the length of the curve by simply subtracting the station of PT to and the station of PC. So that will give us the length of curve, which is 510.68 meters. Okay. So once we have computed for the curve, we can now compute for the radius of curvature. So R from your surveying is equal to LC, the length of curve divided by the given intersection or central angle. So R now is equal to 510.68 divided by 80, and you convert this to radians. Okay, so the 80 degrees is converted to radians. So R now is equal to 365.75. And we know that for our design for horizontal alignment, we have to identify the distance or the distance between the center of the curve and the middle of or the center line of our roadway. So for that, our minimum radius will now be equivalent to our computed R minus 1/2 of our lane width, which will give us 363.998, or we can approximate it at 364 meters. Okay, so once we have computed for your R mean, we now check if our side friction is correct or is safe. So with that, we apply now our equation of radius, minimum radius of curvature from our previous discussions. So we have v squared, and the v squared given is 80. E is given at 8%. So we solve now for the side friction, which is equal to 0.0584. And this computed value of Fs will now be compared with the recommended side friction for the 80 kilometers per hour speed based from AASHTO 2011. Okay, so we have here table 3.7 showing now our minimum radius using the limiting values of E and F, wherein the maximum value of E is at 8%. So these values are only for E equal to 8%. So we'll have another table if E is a different value. Okay, so let's check. We have the design speed or the posted speed is at 80. So we have 80 kph, or that's 50 miles per hour. And our side friction is equal to 0.40. Should be 0.40. So comparing now, the recommended value 0.14 is greater than our computed Fs. So therefore, the radius and the super elevation are sufficient for 80 km per hour design speed. Okay, so check for the radius, and then from there you check the side friction, so you'll be able to check also your super elevation. So next, what we do is to check now our stopping sight distance. So we're given here a distance of 5.5, which is the distance or the clear distance that we should have so that when a vehicle is at the point of curvature, he'll be able to see the approaching vehicles or other signs on the other side of the road. Okay, so from our surveying, we know that H here, so we want to know the value of H, and MS will be equal to 5.5. We were able to solve for the value of SSD, or we're going to solve now for the value of the SSD. So take note that for MS, that is now equal to the clearance 5.5 plus 1/2 of the lane width, and that will give us 7.25 meters. Okay, so applying now our surveying equations, cosine delta S over 2 is equal to H divided by RV. Okay, so itong triangle na to. So with that, we know that H is equal to the minimum radius RV minus MS. So applying the values, cosine delta over 2 is equal to minimum radius computed 364, MS is 7.25, and computed RV is 364. So we can now solve for the value of delta, which is 22.91 degrees. So from there, we can now solve for our SSD by multiplying the delta to the radius of curvature. So SSD now is equivalent to 145.54 meters. Okay, so compare this value with the recommended SSD from AASHTO 2011. So we are given this table. So our design speed is at 80. Equivalent design speed is 130. So comparing it, the recommended minimum SSD for 80 kilometers per hour is 130. So it is less than the computed SSD, which is 145.54. Meaning, minimum ito, mas malaki yung na-solve. Ibig sabihin, the SSD is sufficient at 80 kilometers per hour. So it means that our horizontal alignment is okay with regards to the design speed. So next step is to check now our vertical alignment. So using the diagram for the vertical alignment, so we have here the station of the point of curvature and the station for the point of tangency. So we're given your grade 1 and grade 2. We're also given the station of the point of intersection. So what we do is to check first for the value of K. So for K, to solve that, we apply L over A. So we need the value of L, and L will simply be computed as the difference between the stations of PVC and PVT for the vertical alignment. So that's 573 minus 426, which will give us the length of 146.34 meters. Okay, so with that, applying now the equation, we have computed A already a while ago. So K is equal now to 24.39 meters. So again, we compare our computed value to the designed K from AASHTO 2011. So we are in meters. So we use the metric table. So design speed is at 80. Design K should be at 30. So compare the computed K with our value from the table. K at 80 should be 30. It's greater than your computed value of key. Therefore, the key value is insufficient. Okay? But the crash occurred during daylight. And take note that for sub-vertical curves, the sight distances will be governed by nighttime conditions. So, ibig sabihin, kahit insufficient yung key natin, but since the accident happened in the daytime, it will still be a safe speed for the vehicles. Okay? So, meaning, there is no problem with the geometric design. Okay? Pero kung nangyari yung accident during the nighttime, then this finding that the key value is insufficient would mean that there is something wrong with our design. Okay? So in that case, we would now recommend as highway engineers to check other causes of the crash. So it could be human error or vehicle malfunctions. Okay? So that's it for our applications for sag vertical curves and the combination or coordination of horizontal and vertical alignment. So thank you for listening. These are now our references.